So these are three problems that each have a different flavor. The first problem asks you to solve an equation. The second problem asks you to multiply a pair of expressions together. The third problem asks you to factor. The first thing that I'll mention before we look at these problems individually is that the words, the prompt words that are used, should give you a clue as to what kind of answer you're looking for. So what do you think is the biggest difference, for example, between the first problem, which asks you to solve, versus the second and third problems, which ask you other things? So what's going to be the biggest difference in the kind of answer that you have? What kind of answer do I get for number 1 that's different from the kind of answer that I get for 2 and 3?
An actual number.
That's right. So when the problem asks you to solve, and solve is a word that we only use when there is an equal sign, an equation going on, the answer to those questions typically are numbers. Maybe one solution, maybe more than one solution, but the solutions should be actual numbers. Whereas the solutions to 2 and 3 are generally expressions, right? They have variables in them, possibly exponents, coefficients, all that stuff going on. But when the question asks you to solve, you can be pretty sure that your answer is going to be a number. So I want to really quickly just run through the strategies for checking these, and then we'll look at each one of these in turn. So any problem that asks you to solve, again, you're going to get some number for your answer that is supposed to satisfy the original equation that you were given. So to verify your answer in a problem that asks you to solve, all you have to do is plug your answer back into the original equation. Right? So just take the moment and put it back into the original equation and see if it balances both sides. So that's how we'll check our answers to question number 1. The second problem type asks us to multiply. And while it's a little more difficult to check your actual answer, one of the most important things that you can do to check your process when you're multiplying two polynomials together, as we are here, is to check and make sure that you did the right number of multiplications. We'll talk about how to do that. Check that you have the right number of terms, because that tends to be where people slip when they slip in multiplying polynomials. And then problems that ask you to factor are among the most challenging that we do in algebra. But fortunately, they have the most straightforward way to check your answer, and that is just to go backwards, to re-multiply, FOIL out your answer, and see if it gets you back to where you started. After all, factoring and FOILing or multiplying are nothing more than just the opposite processes to one another. So whatever one does, the other one is designed to undo. So we can almost check our answer in a factoring problem by re-multiplying our answer back out. So starting with question number 1, where we solved an equation, we got these purported solutions, x equals 6, x equals -1, and if I want to check that those answers are indeed correct, I can just plug them back into the original equation. So let's do that. So for the first, let's get the equation up here, x squared minus 8x equals 6 minus 3x. And we think that the answers we wanted were x equals 6 and x equals -1. We would have to check them both if we wanted to be absolutely certain, but in the limitations of time, let's just check one of them. Let's check x equals -1 to make sure that that actually is a valid solution to this equation. So all you need to do is plug it back in, and whenever you plug a number into an expression, hug it with parentheses, just so you don't commit the sign errors that are so tempting to commit. And I'll just put a -1 in here everywhere we see an x. Equals 6 minus 3 times -1. And then all I have to do is evaluate the left-hand side, evaluate the right-hand side. What's -1 the quantity squared? -1 times -1, yeah, positive 1. And then I have minus 8 times -1. That's minus -8, right, which is plus 8. And then I have 6. And then I have minus 3 times -1. Give me a plus 3. And so what do you conclude about x equals -1? Solution or not a solution? Solution, because it made both sides of this equation the same. It made the left-hand side 9, and it also made the right-hand side 9. So anytime you're solving an equation, this also goes for systems of equations, by the way, plugging your solution back into the original is the gold standard for verifying an answer. And again, it's always better for you to catch any errors than it is for me. Real quickly before we move off of this problem, let me re-sketch the overall strategy that you probably used to solve this equation. X squared minus 8x equals 6 minus 3x. What was the most important part of the first step of your strategy here? Getting everything equal to 0, exactly. Before we can do anything with an equation with a degree higher than 1, like x squared, right? We need to make one side of the equation equal to 0. And how do you accomplish that here? So we're going to move the 3x from one side of the equation to the other. And this may be another place that's tempting to commit a sign error, but if I want to move these minus 3x to the left-hand side, I need to add 3x to both sides. So that's going to give me negative 8 plus 3, that's negative 5, is going to be the coefficient of x on the left now. And then I still have x squared, I still have a 6 on the right. And then what? Yeah, exactly. My priority is getting a 0 on one side of this equation. So I need to subtract absolutely everything from one side to the other. And once I've done that, now is the time to take the next step, which was factor. Never factor in an equation before the other side of the equation is 0. Otherwise, your factorization is going to be useless, because you can't do this splitting that we did here unless the right-hand side of the equation is equal to 0. So that is the time to factor, x minus 6, x plus 1. And then split those two factors each into their own equation and solve from there. X equals 6, x equals negative 1. Okay, so but again, the most important part about this is checking, right? Check your answer, plug it back into the original equation. For the second example, I want to actually come back to the second example. Let's talk about the factoring example first, because it has the more straightforward means by which to check. 6x squared minus 5x minus 4. This is a tricky factoring problem, but I'm claiming to you that the answer, that a factorization of this, is 3x minus 4 times 2x plus 1. So how can we check that that factorization actually works? Foil it. Multiply it back out. Do the opposite of factoring. Now, when I FOIL, I like to do it with this nifty little mental device where I keep track of things by putting them in a grid. This actually looks a lot like, quote, the new math, or Common Core math, or whatever you want to call it, that's being taught in the earlier grades now, with a good reason, because I think the reason that they teach multiplication in this way in the lower grades now is to make this process more familiar when people get to algebra a little bit later on. But here's how it works. I want to FOIL out the product 3x minus 4 times 2x plus 1. So when I do that, I end up needing to multiply the first term by the first term, the f in FOIL, the outer terms, the 3x and the plus 1, so that's what I'm going to get here in this little cell. The inner terms, negative 4 and 2x, I'm going to put that here. And then the last terms, plus 1 times minus 4, I'm going to put there. So that's kind of how this grid correlates to using FOIL the usual way. And when I carry out those multiplications, what do I get for 3x times 2x? 6x squared. Right, so the 3 times the 2 gives me the 6. X times x gives me the x squared. The exponents adding because we're multiplying the powers. Right? X to the first times x to the first is x to the 1 plus first, x squared. Now in the O box, 3x times 1, 3x. The I box, negative 4 times 2x. Yeah, negative 8x. And then L box, plus 1 times minus 4. Will give me negative 4. Now, it's just a matter of adding up all of those terms. So 6x squared plus 3x minus 8x minus 4. How do I finish simplifying that expression? 3x and the minus 8x are like terms. So I can combine them together by doing what? Adding the the coefficients together. So positive 3 added to negative 8 gives me negative 5. And sure enough, that's exactly the expression that we started with, 6x squared minus 5x minus 4. So any factoring problem, check it by refoiling it, remultiplying it back out, and verify that you get back to where you started. And if you prefer to use FOIL just by sort of sketching in the little jumping dolphin arrows or whatever you want to call these, that's fine too. I happen to like this grid for a reason that hopefully I'll convince you of in our final example before we start the exam. Let's talk about the the multiply problem, just to make sure we get to all three of these. So for the multiply problem, you're asked to multiply x squared plus 2x plus 4 times the quantity x minus 2. And then you told me that the answer that you got was x to the third minus 8. And I want to agree with you, because this is a correct answer. But how can we check that we did this problem correctly? Unfortunately, there's not a good way to do it just from the answer. So you have to look back into your process. And that's where this little grid comes in even handier. Because when you're multiplying polynomials together, when we're using what we might call an extended version of FOIL, we need to know that every term from the first factor, x squared plus 2x plus 4, has been multiplied by every term from the second factor, x minus 2. And this grid is a way of bookkeeping, a way of keeping track of that process so that you don't miss any terms. Because a very common error in doing this that I saw from some of you on the first exam is that you kind of just multiplied maybe the 2x and the x and maybe the 4 and the minus 2, and then that was it, right? You didn't do enough multiplying. When really, we need every term from the first factor multiplied by every term from the second factor. And so how many total multiplications do we expect to have to do here? How many cells are in this grid? 6. Because I had 3 terms from the first factor, and I had 2 terms from the second factor.
So you're really just distributing x minus 2.
That's exactly right. Yep, we're distributing x minus 2, and then sort of distributing backwards across the x minus 2 to make sure that everything from the first factor and everything from the second factor are accounted for. So when we do this multiplication, we'll get from the product of the x and the first term, x to the third plus 2x squared plus 4x. And then when the minus 2 distributes across, we'll get minus 2x squared minus 4x minus 8. Again, each of these products just coming from multiplying what's on its row by what's on its column. And then finishing the problem just by combining the like terms. Well, what are the like terms that you see here? What
-2x squared plus 2x squared.
There we go. So those two like terms combine together to give me how many x squareds? 0 x squared. In other words, they so-called cancel, right? We end up with that term vanishing in our final answer. Okay, any other like terms here?
-4x plus 4x.
-4x plus 4x, which when they combine together also give me 0, right? 0 x's. So those cancel one another out as well. And so the only terms left standing are the x to the third minus the 8. So there we kind of had to go back through the process that we used in order to check the answer, but I find that it's a useful heuristic, a useful verification step to ask, how many terms did I expect to have in my product based on the number of terms that were in my original expression? And because I was multiplying a trinomial by a binomial, something with 3 terms, multiplied by something with 2 terms, I have to expect that there will be 6 multiplications along the way, even if my final answer doesn't have 6 terms in it necessarily. Right? This final answer only had 2, but that was after we simplified, after we combined all the like terms that we could combine.